Okay.
Okay. Hey everyone, we're UCI CanSat. Basically, our competition, we're an international competition, MA competition, where teams from around the world compete to design a canister-shaped satellite capable of completing a descent from 700 meters. You can see up on our diagram how the CanSat is composed of a payload and a canister. So both payload and canister get released from a rocket at 700 meters, and then it uses a parachute to descend at 20 meters per second. Once it reaches the altitude of 400 meters, there's a separation phase in which the payload is separated from the canister. After it's separated from the canister, we have two autogyro blades that will fold up, and then they will rotate, and that will cause the payload to fall at a velocity of 10 to 15 meters per second. Previous work from our team, last year's team focused on designing a controlled descent of a payload safeguarding an egg as it's what's been contained in it. Basically, they had an aerobraking shield and a parachute mechanism, and one of the goals for the project was to deploy the aerobraking shield during their descent phase. Last year's team was able to get first place in their preliminary design review and their first place in their critical design review phase. However, they got 17th in the overall competition after the launch, and that was due to electrical problems that they encountered on site, bad case of Arduinos. So basically, our goal is to improve on last year's success and avoid last year's mistakes to perform well in the CanSat competition. So for some more goals for this year is we want to place in the top 10 in the PDR and the CDR, the design reviews, because those reviews kind of determine who gets to go on to the final competition, so we need to do well in those. The CanSat competition is actually in Texas this year, and so we're going to work on traveling over there. Additional goals, we want to make sure all our team members have practical experience in the engineering design process, and we really want to be able to represent UCI at our international competition in Texas. Shown here is our objective tree. Basically, we have one primary objective to perform well in the CanSat competition requirements, and that's broken down into 4 different objectives, which is from there it's broken down even more. A couple of our sub-objectives are to receive and transmit accurate data at 1 hertz from the CanSat to the ground station, and also we want to be compatible with the competition launch system and requirements. And I'll pass this on to Edwin.
Here you can see it's a look at our organization. As you can see, we have our advisor and our 3 team leads for hardware, operations, and software. Below them, you have each individual member and the teams that they contributed to the most. From this organization, you can see that even though different members are in different teams, we still have to communicate with each other to essentially maximize performance for the overall CanSat competition. As for communication, we primarily use different applications. We use Slack to essentially communicate between groups and different subsystems, GitHub to update any files, and a Google Drive where we can work on documentation together. We also have a GrabCAD where we can modify and update different CAD designs that we come up with. We also streamlined processes within the CanSat, such as purchase management, power budgets, and Gantt charts. Essentially, the CanSat can be broken down into 2 different design aspects, the hardware and the software. And within the hardware and software, you can break it down into further subsystems. For the hardware, the one subsystem is the overall mechanical, and this includes designing for the structure of the CanSat, the payload, the container, as well as the autogyro propeller design and the release mechanism for that. And we just have to make sure that the structural components meet the requirements of competition. And we also have the electrical subsystem, where it's essentially battery and printing, designing, and assembling a printed circuit board. For the software, we have the ground station and the flight software. For the ground station, we have to ensure that the ground station software receives the telemetry data at 1 hertz. And for the flight software, we essentially have to program the Arduino and make sure that it's transmitting the telemetry data at 1 hertz and that we can receive it. Here for the CanSat project, there's 3 main deliverables. We have the preliminary design review, the critical design review, and the actual CanSat hardware for competition. As you can see, these are different aspects of each deliverable that we have to discuss. And the blue ones are the ones that we've already completed or are working on, and the white ones are the ones that we still need to work on for the future, for the critical design review and the CanSat hardware. Here's an overall milestones. Essentially, it displays all of the deadlines that we have set by ourselves, 189 for the CanSat competition. Our next up deadlines are we have to have a completed prototype by March 10th, and we also have the winter design review by March 15th. some of the design requirements, since our project is a competition, we have to follow the project requirements set out by the CanSat mission guide. Some of them, these are some of the overall requirements, but in total I believe we have around 54 requirements that we have to meet. The most important ones are obviously that the CanSat has to weigh 500 grams, give or take 10 grams. It also has to fit within a cylindrical envelope of 125 millimeter diameter and 310 millimeter length. Also has to not have any sharp edges. It can't interfere once it descends. It has to use an auto gyro to descend, and it has to have a descent rate for the parachute and for the auto gyro specified by the CanSat requirements. Here, I pass it on to Parth.
Thank you, everyone. So in regards to progress in this quarter, with the payload structure, we have finished the fabrication of our payload structure. This is the structure where all the electronics and all the sensors are mounted to. And we, for the material, we use carbon fiber, which was CNC cut, and then we epoxied the carbon fiber pieces together. Our weight for this structure is actually 39 grams, and since weight is a really heavily requirement that we have to abide by, it's nice because this is actually less than our estimated 46 grams. We actually lowered the placement of the middle plate before. When in our actual design it was in the middle, but however we lowered it to lower the CG of the actual satellite. This provides more stability when the satellite is descending. So for our next steps, we're just going to begin mounting all the electrical hardware and the sensors to this actual structure. We're going to actually do some mechanical and environmental testing as outlined in the CDR, and we're going to compare all this testing to the simulations we've done prior. In regards to the actual container, this is where the science payload sits in and is separates from during the competition. So we 3D printed 2 of the end caps and the top of them, and we actually designed a parachute release mechanism, a different one, and we have. So the weight actually is more than the expected 70 grams, so we have to design, actually account for this by maybe lowering the infill of the 3D printed parts, lowering the thickness, etc. So that's one of the main problems we have. And we're going to try to 3D print and assemble the actual parachute release mechanism now, so that is going to be happening in the future. And last but not least, in the mechanical aspect, we're going to look in for the descent control. All the parts have actually been received and able to actually, except for the propellers, which are going to be ordered based on the design and the calculations for our descent rate. So we've 3D printed a couple of the components, such as the bearing block. Our next steps is we're going to start press fitting the bearings into the bearing block and assembling the components onto the payload structure. We're going to place the purchase orders for the propellers, and then all other, basically any minor design changes, we're going to make sure there's nothing wrong with those. And now I'll pass it off to Emmy to talk about the PCB and ground station.
Alright, so this is some more of our progress. This is our software progress for our ground station software and our CanSat's flight software. So the ground station has to receive data in real time from the CanSat as it's descending. It has to show the data, it has to show some data plots. We have it showing numeric data as well. So our current progress is that we can successfully receive data from 2 sensors using our XB wireless modules, which is what we would use during the competition. This is actually our current ground station that our software team has developed. Now that we have that working for 2 sensors, we can begin integrating the other sensors, the rest of them, into the ground station GUI, showing more data and adding additional features such as saving the data, which is a requirement for the competition. And this is some example data here where it's showing the GPS satellites being tracked for the GPS readings. It's showing the altitude, and it's showing a roll and pitch from a gyro sensor. So this is our electrical progress. For electrical system, we've successfully assembled our first PCB. This means our electrical design has been validated, and we're currently building more PCBs for our software team to use in their ground station and flight software development. So the PCB is basically a specialized version of an Arduino. It's actually programmable with the Arduino IDE. You don't need any special software to program it or interact with it. What makes it interesting is that it has all of these header pins for the sensors that we selected. So that's our pressure sensor that we selected, and it plugs directly into the PCB. These headers connect to the XB wireless module, and that way we reduce the amount of wiring, and therefore we reduce the weight of our electrical system, and the amount of like wiring errors and messy wiring and difficulty troubleshooting. And we chose to develop a custom PCB this year, even though it seems like a lot of work and a lot of technical risk, because last year we had, as previously mentioned, a lot of problems with our electrical system that turned out to be due to counterfeit Arduinos, due to having all of our off-the-shelf parts wired together, and then the wires were constantly coming loose and they added a lot of weight, and they made it extremely difficult to get to the root cause of the issue, which was that we actually got counterfeit hardware from Amazon, no less. But this year we have the PCB, we know exactly what's on it, and it's been a lot easier to troubleshoot. So this is our budget. This is our engineering costs for like components, equipment, materials, etc. We currently have managed to cover all of our engineering costs with UROP and 189 funding. This is actually our current costs, so we expect them to increase over the rest of winter quarter and over spring quarter as well. Our engineering costs are covered, but our travel costs are not, and we currently need funding for the costs of attending the CanSat competition at the end of spring. So you see, when we add up all our current engineering spending, we end up with a surplus, but on the next slide, when we add in the travel, we end up with a huge deficit. And this is because of the cost for 10 students, our whole team, to attend a competition. For room and board at the competition, it's $250 each. That's subsidized by the CanSat competition. It's the lodging and food for the whole weekend. And then air travel to get to and from the competition, which is held in Texas, is we estimate another $350 per person. So right now we've been unable, for various bureaucratic reasons, to apply any of the funding we have towards travel expenses. So we're still looking for ways to meet that cost. Just to go back to the bigger picture, CanSat is a multidisciplinary project. We have MAE students, but we also have 2 CS students on our project. We also do electrical things, as shown by the PCB slides. So our software team actually works on hardware as well. They work on building the PCBs, troubleshooting them, and our hardware team participates in software on making sure their hardware can interface with the software and be controlled by it. So CanSat is multidisciplinary, and it also encourages students to take kind of ownership of their work. Because we're a very small team, everyone has to take an active role in managing the project. Everyone has to assign themselves tasks. Sometimes keep a lookout for trouble, make sure the project is proceeding. So I think having the small team actually benefits us in that way. And that's the end of the presentation. Any questions?